So law of cosines is extremely important because it makes solving non-right triangles a lot easier. And it's wonderful to be able to use these equations, but to know where they come from is extremely powerful. So let's go ahead and see if we can't prove why this equation works. And in order to do so, we need to start with a bit of given information. So here is what's given. We're given side length C, we're given side length B, and we're given angle A. And our ultimate goal is to find an expression to solve for side length A. So go ahead and take a moment, pause the video, draw this out so you can follow along with me. So dealing with non-right triangles is pretty difficult. So usually the first step that we're going to take is take this non-right triangle and we're going to drop an altitude. So an altitude is when you go from the very, very top of it and you make a perpendicular perpendicular line to the base of the triangle. So now we've created two right triangles from one non-right triangle. And to help you see those triangles better, I'm going to go ahead and outline them in a bold line. So there's the altitude that we dropped. And over here, we're starting to create the first right triangle. And I'm going to outline the second one in yellow to kind of give it a good stark contrast there. So here are our two right triangles, and this is the basis of it all. For the sake of being able to work with things, let's go ahead and call this altitude h for height. And what we're going to do as well is we're going to split this bottom part. Now the whole thing is c, so semi-arbitrarily, not really randomly, but for the sake of this proof, we're going to go ahead and call this side length x, which means this side length over here has to be c minus x. If the whole length is c and this part right here is x, that means this is c minus x. So what's really nice about this is that because we have two right triangles, we're allowed to use Pythagorean Theorem, and we're allowed to use those trig functions, so SOHCAHTOA. Both of those are fair game now, as long as we use them with separate right triangles. So I'm going to start by using this blue triangle to do Pythagorean Theorem. And I'll explain why I'm going to do that in just a moment. But I know the hypotenuse squared is equal to the two legs of the triangle squared, c minus x squared, added together, h squared. So here's the two legs of the triangle. This is essentially a squared plus b squared equals c squared. Just looks a little bit more fancy. And I know that this is very counterintuitive, but let's go ahead and expand this. I'm going to multiply c minus x times c minus x. So a squared is equal to, and I'm going to go ahead and do this off to the side. I'm going to erase it in just a moment, but in case you've forgotten, c minus x times c minus x, you have to use that distributive property, or FOIL. That's kind of the lower level way we say we distribute it. So c squared minus, multiply negative cx minus cx plus x squared. So it ends up being negative 2cx plus x squared. So you can also prove this using Pascal's triangle, but for now we're just going to go ahead and accept. That's minus 2cx plus x squared, and we still have that plus h squared off to the side. So we used Pythagorean Theorem on this blue triangle, and we end up getting this really nasty equation. So for now, that looks kind of nasty, but we'll go ahead and see what happens here. So part of the reason that I know to do that is because I'm ultimately looking for an expression for a. Well, now I have a squared equals something over here. So if I can find a way to get rid of these x's and h's, then I have an equation for a. So I'm going to start by looking at this yellow triangle over here now. And I'm going to go ahead and do Pythagorean Theorem for that as well. I'm going to say that the hypotenuse squared is equal to h squared plus x squared. Now what's interesting about this is somebody realized that if you solve for one of these two variables, really doesn't matter which one, I'm going to go ahead and solve for x. If I solve for, x squared, if I solve for x squared, then I see that x squared is equal to this b squared minus h squared, And I also see x squared right here. So I can actually substitute in. Instead of writing x squared, I'm going to write b squared minus h squared. So I'm going to use a little bit of color to help you guys see this, but I have not touched anything except for that x squared. 2cx plus, and this is where I start putting in the new stuff, b squared minus h squared plus h squared. And what's so nice about this is that if you look right here where my pen is, I have negative h squared and positive h squared. Well, those two cancel each other out. And I end up with a squared equals c squared minus 2cx plus b squared. So I just went from having 3 unknowns in my equation to just 1. I used to have an x squared, and an h squared. Using the substitution with the yellow triangle, I brought it down to where all I need to do is find a way to get rid of this x right here. Well, I have no more triangles to use Pythagorean Theorem on, but somebody else discovered, well, if we take this angle right here, remember this was given, that was given to us, we can use cosine. If we take the cosine of that angle, well, cosine of capital A is equal to adjacent x over hypotenuse b, which with a little bit of rearranging, cosine of A, b cosine of A equals x. And we were just looking for a way to get rid of that x. Well, now we know x is equal to b cosine of A. So one last substitution on into here, and I'll go ahead and use those colors. A squared equals c squared minus 2c, and this is where we substitute in that x, b cosine of A, b, oops, sorry, wrong color, green, b cosine of A plus b squared. We have our law of cosines. Now, I'm going to go ahead and rearrange just a little bit, just so that it's in our standard form that we're used to. A squared is equal to b squared, so I'm going to move this b squared up front, plus c squared minus 2bc cosine of A. So that right there is our derivation, or our proof, of that law of cosines. Split it into 2 right triangles, use Pythagorean theorem on the left triangle, then on the right triangle, and substitute on in. And then using SOHCAHTOA on the right triangle, you can figure out what x is equal to, and you throw a little bit more substitution and rearranging, you get a nice, easy form of that law of cosines.